9.3 Vector Valued Functions. In this lesson and the next, we will explore the vector form of the parametric equations x equals f of t and y equals g of t, where f and g are continuous functions of t on an interval I. At this point, we have only considered functions where the domain and range are sets of real numbers, or real valued functions. Recall that plane curves were defined by coordinates at time t as f of t, g of t. Now we want to represent motion along a curve by giving a definition to a vector-valued function where the domain consists of real numbers and maps the range to a set of vectors. Maps the range to a set of vectors. So in 2 dimensions, a vector-valued function can be represented in the form r of t equals, and these symbols like right here represent a vector. So the vector f of t, g of t, and or as r of t equals f of t I plus g of t j, and ij is the unit vector. I don't know if you remember that from physics, but you can think of it as one I plus one j. And so basically, if we're talking about this point, f of t, g of t, it's f of t along the x-axis, and then g of t along the y-axis. Okay, so, and that's how you get to that vector. But you start the vector always at 0, 0, and then you go to that end point. Okay, and every single point on this curve C, has a point f of t, g of t at the end of that vector, okay? And that's how it's formed. So where the component functions f and g are real valued functions of the parameter t. That is, the domain of a vector function is the set of all t for which both component functions x equals f of t and y equals g of t are defined. So the domain of a vector function is the intersection of the domains of the component functions f and g. So we will talk about what that means in our examples. The domain of a vector function is the intersection of the domains of the component functions f and g. So then, to geometrically represent a vector-valued function in 2D, place the vector r equals r of t with its initial position at the origin, and then as t varies, the tip of the radius vector r will trace out the curve C. Since the vector equation r of t equals the vector f of t, g of t is a set of parametric equations, C can also be called the graph of the parametric equations. So arrowheads along the curve indicate the orientation of the curve at the increasing values of t. So if you see, I'm just going to erase what I did there, and if you see these arrows here, that means that that is the position, it's starting like, let's say it started here or something, and it's going this way with those vectors, okay? So that's the direction in which it's going. So example number 1, express the parametric equations x equals 2 cosine t, y equals t plus sine t as a vector-valued function. And so there's 2 ways to represent it. One is in vector form. So we could say that r of t equals, and then we would represent vector, and it would be the x value, 2 cosine t, comma, the y value, t plus sine t. And that is with those vectors. Or you could represent it, r of t equals 2 cosine t times I plus t plus sine t times j. And a lot of times we call them I hat, j hat. So if you want to call it that, I think that works too. So example number 2, given the vector equation r equals t squared plus 1I plus ln 2 minus tj, find the following. X equals f of t. Well, we know that the x is multiplied by the I, so our x equals t squared plus 1, okay, and our y is going to be what's being multiplied by the j. It's going to be ln of 2 minus t. And then what is the domain of r? Well, the domain of f, okay, which is our f of t, which is our x, right? Which seems weird, but it's our x function. For that vector, that domain is everything, negative infinity to positive infinity. And the domain of g of t, which is our y, is going to be, we're going to take that 2 minus t and say it has to be greater than 0. And so we could add t to both sides and read it backwards. T is less than 2. So that would be from negative infinity to 2, non-inclusive. And when we look at these, I guess I forgot to put y there. When we look at these together and do the intersection, the domain of r is going to be the intersection negative infinity, comma 2. Okay, that is the intersection. Which one do they share? So, we said, just to recap this, and I'll do this in a different color to recap it, we said that the domain of our f of t was negative infinity to positive infinity. The domain of our g of t was negative infinity to 2. And so that made the domain of our r of t, which is the intersection of those two domains, negative infinity to 2. Okay, so that was what they were asking for. So for part A, they wanted us to give them this. And of course, this was also called our f of t, right? And this one was called our g of t, okay? And for answer to part B, negative infinity to 2. Okay. Next page. Example number 3, sketch the plane curve represented by r equals 3 cosine ti plus 4 sine tj from t equals 0 to 2 pi. Use arrows to indicate the direction and write the rectangular equation. Okay, so if you wanted to, we could make our t and our x and y. 0, let's say pi over 2, pi, 3 pi over 2, and 2 pi. And of course, our x is our 3 cosine t, and our y is our 4 sine t. So 3 times the cosine of 0 is 3, and 4 times the sine of 0, is 0. And then 3 times the cosine of pi over 2 is 0. 4 times the sine of pi over 2 is 4. 3 times the cosine of pi is negative 3. And 4 times the sine of pi is 0. 3 times the cosine of 3 pi over 2 is 0. And 4 times the sine of 3 pi over 2 is negative 4. And then 3 times the cosine at 2 pi is 3. And 4 times the sine of 2 pi is 0. So it's going to start here at the initial point of 3, 0. It then moves to 0, 4. Then it moves to negative 3, 0. Then it moves to 0, negative 4, and back. Okay? And so I'm going to just sketch this. And put arrows on it. so that if someone was looking at this, they would know what direction this was being sketched. Okay, and we could put that this is your start and your end. Okay, that 3, 0. It's your starting point and your ending point for those t values. And if we were going to write this as a rectangular equation, I would divide by 3, divide by 3. This would give me x over 3 equals cosine t. I would divide by 4, divide by 4. This would give me y over 4 equals sine t. I would square both sides. This would give me x squared over 9 equals cosine squared t. I would square both sides of this one. Y squared over 16 equals sine squared t. And then I would add them together. And remember that when I add my cosine squared plus sine squared, it gives me the Pythagorean identity 1. So I add those, and then I change my sine squared plus cosine squared into 1, and that's my rectangular equation. Sometimes we call it the Cartesian equation, or the rectangular equation. Okay, it's basically it in terms of x and y. If these bottom two numbers would have been the exact same, or, you know, like you can look at this as 1/9 times x squared plus 1/16 times y squared. If those would have been the same, it would have been a circle. Okay? All right, let's move on to the operations of vector-valued functions. Since vector-valued functions are the sum of the parametric components x of t plus y of t, we can perform the following algebraic operations. Likewise, limits, continuity, and derivatives are also defined. So if I'm taking the sum or the difference of a vector-valued function plus another vector-valued function, I would just take my f of t I plus g of t j and add my my second f of ti plus my second g of tj. So you could actually add the f1 of t and your f2 of t together and factor the I out, and add the g1 of t and g2 of t together and factor the j out. Scalar multiplication: when a constant k is multiplied by a vector-valued function r of t. That is the same thing as taking that k and multiplying it by the f of ti plus g of tj. And if we distributed it, it would be k f of ti plus k g of tj. If we are multiplying a function times a vector-valued function, so h of t times r of t, it's the same thing, h of t times the f of ti plus g of tj, which you would distribute to h of t times f of ti plus h of t times g of tj. If you are doing the dot product of two vector-valued functions, it is equivalent to the dot product of those functions as, you know, in that form of times I times j, as they've shown you here. And then you could look at it as that when you take the dot product of the f1 of ti plus g1 of tj, dot product f2 of ti plus g2 of tj, you get f1 of t times f2 of t plus g1 of t times g2 of t. And then your limits. The limit as t approaches some a for this vector-valued function is the same thing as the limit of the f of t as t approaches a times I plus the limit of the g of t as t approaches a of j, or times j, I should say. Derivatives. If I take the derivative of a vector valued function, it is the derivative of the first function times I plus the derivative of the second one, the g of t times j. A vector valued function is continuous at a point t equals a if the limit as t approaches a of that vector valued function r of t equals r of a. And a vector valued function is continuous on an interval provided r of t is continuous at every point in the interval. Okay, so that leads us to example number 4. And it gives us a scenario that my first vector valued function is t squared I plus 3t minus 2j. And my second vector valued function is 3t squared minus 1i plus 4tj. And then I also have just a regular h of t equals 2 over t function, okay? So find the following. They want us to find r1 of t plus r2 of t. And remember we said that if we take our r1 of t, which is our t squared I plus 3t minus 2j, and added it to our 3t squared minus 1i plus 4tj, that I could add the parts that are the I. So I can say, well, I've got t squared plus 3t squared minus 1 times I, plus I've got my 3t minus 2 plus my 4t all times j. And then when I add those, I get 4t squared minus 1 I plus, this would give me 7t minus 2j. And that would be my answer to that sum of the vector valued functions. So you basically just, add your I, or add the ones that are being multiplied by I together times I, and add the ones that are being multiplied by j together times j. Okay, now we go to the dot product. And for this one, it's going to be equivalent to, I've got my t squared I plus 3t minus 2j, and then the dot product of 3t squared minus 1i plus 4t, sorry, I'm running out of space here, j. And this is going to give me my t squared times 3t squared minus 1, and then plus my 3t minus 2 times my 4t, which is going to give me 3t to the 4th minus t squared plus 12t squared minus 8t. And then I add my like terms, 3t to the 4th plus 11t squared minus 8t. This would be your final answer, and this is in terms of a scalar. So I do want you to remember that this is dot product multiplication that would give you a scalar. Okay? I'm going to change my color. Now, this time I've got the h of t just being multiplied by the r1 of t. So it's like a regular function times a vector valued function. My regular function is 2 over t times my vector valued function of t squared I plus 3t minus 2j. And so what we do on this one is we're just going to distribute and multiply, giving us 2t I plus, and when I distribute here, I get 6, because my t's would cancel on that first distribution, and then minus 4 over t j. This double bar is like a distance equation. Your r1 of t minus your r2 of t. This is like your distance equation. So if I did my double bar, my r1 of t is that t squared minus our 3t squared minus 1. So you're basically taking the x of your r1 minus the x of your r2, and then plus the y of your r1 minus the y of your r2. And this is going to be the square root of, we get negative 2t squared plus 1 squared plus, and then this one, because you have to kind of add those together like that, is going to give you negative t minus 2 quantity squared. And then I went ahead and multiplied those out. So I got 4t to the 4th minus 4t squared plus 1. Oops, sorry about that. And then when I multiply this one, I get positive t squared. I get positive 4t. And then I get plus 4. Which is going to give us the square root of 4t to the 4th minus 3t squared plus 4t, and then plus 5. Okay, which leads us to example number 5. This one is limits. The limit as t goes to 2 of the vector valued function 4ti plus 2 over t squared minus 1j. And so we're basically putting the 2 in for t, giving us 8i plus 2 over, this would be 4 minus 1, 3j. And that is your limit. This one, again, you're going to be looking at approaching or substituting in pi. So the cosine at pi is negative 1. So that would be negative 1i. I just put plus, but it's probably going to be plus or minus. If I put the pi in for t here, it's sine of pi over 2, which happens to be negative, or no, positive 1. Well, the negative in front of it. The negative in front of it is positive 1. And then j, so this ends up being negative I minus j. Our next limit, if we put 0 in, we get e to the 0, which would be 1, I, plus, and then when we put 0 in here, we get 0, j. Ooh, you know what? I just looked at my work. No, you don't get 0 there. Sorry. Do you guys remember the limit as x approaches 0 of sine x over x being 1? It was this function that looked like this. It had an open circle here, but it was like that. But the limit was 1 as you approach 0. So that's what you're looking at. You're looking at 3 times the limit as t approaches 0 of sine t over t. and then times j. And since this is 1, this ends up being 1i plus 3 times 1, 3j. Sorry about that. And then part D, this is just a different way to show your vector valued function. You know that you could also call it e to the negative t I plus t over t squared plus 1j. And so you can break this up into separate limits if you want. Times I, limit as t goes to infinity, j. And so if I put infinity here, I get 1 over e to the infinity, which that goes to 0. And then plus, here, if I just look at my t over t squared, that's 1 over t. And if I put infinity into 1 over t, that one also approaches 0. So 0 plus 0, 0. And then example number 6. It says, state the interval on which the vector valued function is continuous. So you are going to be looking at the domain of your f, which is, so for this one, your f of t is the square root of t minus 1. Your g of t is going to be negative 1 over t. And you know that for f of t, t minus 1 must be greater than or equal to 0, so t must be greater than or equal to 1. So that one is going to be 1 to infinity. You also had to find out the domain of the g function, and it looks like that's going to be negative infinity to 0, union 0 to infinity. And so if I look at the intersection of these, the domain, I'll put this in a different color, the domain of my r of t is going to be the intersection 1 comma infinity. Inclusive. And then for part B, r of t equals the vector ln t plus 2 comma 1 over t squared minus 4. And so again, you're going to be thinking of, well, what is the domain of my g function, or my f function? Let's do f function first. Ln of 2 plus t, remember, our t plus 2 has to be greater than 0, so t has to be greater than negative 2. So that one's going to be negative 2 to infinity. The domain of my g function, everything except for 2 and negative 2. So negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. And the intersection of those is going to be, because think about this, if the first one was negative 2 to infinity, the second one, I'll do it in a different color. I don't want that green. I will say, okay, the second one is negative infinity to negative 2, which that's not going to be anything that's included. So I don't really need to worry about that. And then it says negative 2 to 2. And then 2 to infinity. So you can see that this is going to include everything but 2. So the domain for my r is going to be negative 2 to 2, non-inclusive, union 2 to infinity. That is the intersection of those two. Okay, that leads us to example number 7. In our example number 7, find each of the following. Given that we have this vector valued function, find the derivative of the vector valued function. So r prime of t is just going to be the derivative of my f of t times I, and then plus the derivative of my y of t times j. So 6t times I minus 5 times j. And then I've got another vector valued function that I need to find r prime of t. This time, we had to, look at that as t to the 1/2. And when I brought it down times the 2, it turned it into 1, t to the negative 1/2, which gives me 1 over the square root of t times I plus, and this one would have been 1 over t cubed times the derivative of t cubed, which would be 3t squared. And then the t squareds go away, so this becomes 3 over t times j. And then part C, given r of t equals t cubed comma 3t squared, find r double prime of t. And so our r prime of t is going to be vector 3t squared comma 6t, and our r double prime of t is going to be 6t comma 6. And then for part D, they want us to find the first and second derivatives again, only this time we have the vector valued function e to the negative t comma t squared. So our first derivative is going to be negative e to the negative t. And the second part will be 2t. And our second derivative, when we take the derivative of the first derivative, it's going to put us back to e to the negative t, comma 2. And I just noticed this is a dot product. So this is r prime of t, dot product r double prime of t. And so that's going to give us negative e to the negative 2t plus 4t. And remember, this is a scalar. Okay. And so now we get into our derivative rules, which the rules for differentiation of single variable calculus can be applied to vector functions. There is a product rule for the dot product. Assume that u and v are differentiable vector valued functions of t and k as a scalar, then the following properties are given. So if I take the derivative of some constant k times u of t, it's just the constant k times u prime of t. If I had the sum or difference of two vector valued functions, it's just going to be that I'm taking the derivative of. It's just going to be the derivative of the first plus or minus the derivative of the second. If I have the derivative that I want to take of a regular function times a vector valued function, it will be the regular function w of t times the derivative u of the vector valued function plus the regular function u of t regular vector valued function times w prime of t. And then the product rule for vectors, taking the derivative of u of t comma v of t, or times, times v of t equals our u of t times v prime of t plus our v of t times u prime of t. And then our dot product rule is going to be, if I was taking the derivative of that, it would be that first function u of t times v prime of t plus v of t times u prime of t. And then our chain rule, d of t equals u of w of t is u prime of w of t times w prime of t. I think this one, I'm going to talk to you about this one on one of the examples below, just so you can see what happens whenever you do that one. Okay, I'm going to stop and start this again in a minute.